The ZEiTECS ESP Shuttle is a step change in ESP deployment technology designed to reduce operating cost, minimize production deferment, eliminate disruption to operations, and reduce HSE exposure and risk. Let's begin by establishing a few facts about electric submersible pumps, or ESPs. Whether offshore or on land, the demand for ESPs is growing because quite often, ESPs are the only artificial lift method capable of delivering the desired production rate in a particular well system. Unfortunately, ESPs have a limited run life in the deep and hostile wellbore environment, and conventional ESPs run on heavy jointed tubing need a rig or workover hoist to replace. This is a schematic of a conventional tubing-deployed ESP system. The system consists of the pump itself, a seal, a three-phase induction motor, and optional gauges at the base of the motor. The system is powered by heavy three-phase cable banded or clamped to the outside of the tubing. It is the electromechanical complexity of these components that accounts for their limited run life. Imagine this to be the optimum well system production profile, typically declining gradually over the years in response to reservoir depletion and increase in water cut. Unfortunately, an ESP production profile falls far short of this optimum. There are often infant mortalities as a result of the ESP struggling to unload kill fluid and debris left during the workover, and this immediately incurs production deferment and incremental operating expense to replace the failed system. Also, early in well life, reservoir information may be vague, and this will result in suboptimal ESP design and further deferment. Throughout well life, frequent ESP failures continue to incur substantial deferment and operating expense, and even ESPs that do last a number of years will be suboptimal toward the end of their life. All of this results in an average production profile well below optimum, and, in view of the substantial OPEX forecast, a premature economic cutoff. Now imagine an ESP deployment system that would allow ESPs to be replaced without a rig or a hoist. A sacrificial test system could be deployed to clean up the well and measure reservoir productivity, to then be replaced by a system of optimal design. Without a rig or a hoist involved, response to ESP failure would be quicker and more cost-effective. Hence, the average production would be higher and economic lifetime extended. The operator may also like to consider a preventative maintenance program to eliminate unplanned failures and further increase the average production. In summary, the value proposition of rigless ESP deployment technologies is best represented by the areas under these curves. We have mentioned before that conventional ESPs are run on jointed tubing with cable banded or clamped to the outside. The shuttle permanent components are run in a similar way, but at the base of the tubing is a docking station with electrical wet connectors where the ESP may be later inserted. Looking inside the docking station, we see 3 electrical wet connectors and landing shoulders that bear the weight of the ESP and its reactive forces, and also prevent the motor from counter-rotating on startup. We also see a through-bore that permits mechanical reservoir access should that be required. The motor connector, run on the bottom of the retrievable ESP string, has corresponding parts to orientate and connect the ESP into the docking station. The retrievable ESP string consists of a pump, a seal, a motor, and optional gauges. Importantly, these are standard components, readily available from any supplier. At the top of the retrievable string is a seal assembly to provide the necessary isolation between pump intake and discharge, and a bypass valve that may be opened to allow fluid bypass on system retrieval. Also included is an expansion joint to facilitate space-out and to allow installation of a larger ESP system should future reservoir conditions so dictate. If required by the operator's well control policy, a system of valves may be deployed beneath the docking station to isolate the reservoir before the retrievable ESP string is run or retrieved. Then, with the well intrinsically safe, the retrievable ESP string may be picked up either by wireline, rods, or coiled tubing and lowered into the docking station where it automatically orientates and connects. The electrical wet connectors of the shuttle system are highly engineered components. They consist of a series of spring-loaded wiper seals and bellows containing dielectric oil. On every connection, the critical contact surfaces are wiped clean and lubricated to ensure perfect electrical connectivity and insulation. The connectors have been tested to 100 make-break cycles at full pressure and temperature rating in a sandy oil-water mixture. Whether offshore or on land, a rig will be needed to install the shuttle permanent components. In terms of times and costs, the workover is very similar to a standard ESP replacement workover. We will now take a look at the program outline. As we run through the program, we will monitor time, deferment, operating cost, and total cost. So now let's zero the dials. The demonstration case we have chosen is quite typical of desert operations in the Middle East. Following an ESP failure, the operator will likely wait several weeks or even months for a rig to become available and move to location to replace a failed ESP. This incurs substantial deferment. Once the rig has been commissioned, the well must be killed using either the rig pumps or the cementing unit, and flow checks performed. The Christmas tree may then be removed and rig BOPs installed and tested. The old completion string with the failed ESP will then be pulled joint by joint and the tubing either racked back or laid down. It is then quite likely that a bit and scraper run and additional preparatory work will be required before running the new completion. The recompletion starts with the assembly of the lower completion components, which consist of the downhole deployment valve with necessary control lines and the shuttle docking station. The ESP cable is spliced to the pigtails of the docking station in the same way that it is normally spliced to the motor lead extension of a standard ESP motor. A cover plate is then fitted to the docking station to protect the splice before the system is run in whole. The docking station is then lowered on 4 or 5 joints of tubing and set in slips ready to accept the ESP retrievable string. The motor connector, optional gauges, ESP motor, seal, and pump are then assembled and serviced in much the same way as a standard ESP system. Then the expansion joint, bypass valve, and seal assembly are made up to complete the retrievable ESP string. The retrievable ESP string is then lowered into the docking station on a short rod with GS tool and spang jars. Correct orientation and connection in the docking station may be confirmed immediately by testing the cable. The jars may be operated manually to release the GS tool and the rod string retrieved. At this point, if desired, a standing valve may be run and set in the retrievable string to test the integrity of the seal assembly before lowering the system to depth. The docking station with ESP string now pre-installed may then be run to depth on tubing, clamping cable and control lines to couplings and periodically testing electrical integrity in the same way as a standard ESP installation. When pump setting depth is reached, the hanger is made up along with cable and control line penetrators. Then, after confirmation of electrical integrity, the hanger is landed and pressure tested. The rig BOPs may then be removed, and adapter flange and Christmas tree installed. This completes the rig operation, but before decommissioning, the ESP system will be tested and fluids diverted to a local pit. The rig will then be decommissioned and released, but it may still take several days before the flow lines are reconnected and the well is finally put back on production. Now take a moment to look at the time, deferment, operating cost, and total cost of this rig-supported ESP workover before we move on to the rigless replacement. The rigless ESP replacement operation is an altogether different picture. Typically, wireline units may be sourced and moved to location in days, and, while waiting on arrival, a work platform may be erected around the wellhead. Though there may be more elegant solutions, a certified scaffolding structure will suffice. Before system retrieval, the deployment valve may be closed and the tubing filled with kill fluid or water. The Christmas tree cap may then be removed and, if desired, wireline BOPs installed. With the well now intrinsically safe, a standard GS tool is run on wireline with spang jars and sinker bars to engage the retrievable ESP string and retrieve. Once at surface, the components of the retrievable ESP string are laid down and a replacement string assembled. The motor connector, optional gauges, ESP motor, seal, and pump are then assembled and serviced in much the same way as a standard ESP system. Then the expansion joint, bypass valve, and seal assembly are made up to complete the retrievable string. The same wireline tool string with a redressed GS tool is used to lower the assembly into the docking station, where again it automatically orientates and connects. Electrical confirmation of successful landing and connection is immediate. The GS tool is then jarred off and pulled out of hole. This completes the wireline operation, so wireline BOPs may now be removed, Christmas tree cap reinstalled, and wireline rigged down. The deployment valve may now be opened and the ESP started. Now take a moment to look at the time, deferment, operating cost, and total cost of this rigless ESP replacement. The contrast with the rig-supported ESP replacement operation is profound. Though the workover portrayed here involved the replacement of a failed ESP with a ZEiTECS Shuttle system, in reality, the times and costs differ little from those of a standard ESP replacement program. The contrast is even more pronounced offshore, where weather conditions and rig availability incur even more deferment, and rig operating costs are substantially higher. HSE exposure and risk, personnel on board considerations, and disruption to operations are also more significant. It should also be recognized that these comparisons are not only relevant to one event, but to repeated ESP failures throughout well life. This substantiates the value proposition of rigless ESP deployment technologies and the ZEiTECS Shuttle system.